We have seen floating point values and arithmetic related to floating point values. Now we will see how these floating point values can be handled or stored inside a register. The register file that we have discussed are equipped to handle integer values. So we need to have a different setup that can handle these floating point values. So that floating point value is stored, or the register that handles those floating point values are in coprocessor 1, which in short we'll say C1. Now the values that are inside the register file, they are of integer in nature, but values inside C1, they are of floating point in nature. Now let's see a diagram that would show the communication between floating point and integer register. Let's draw a diagram. Let's say this is our register file. Let's in short this is our register file, and we draw another box which is our coprocessor, or in short we call it C1. In register file we have integer registers, and integer registers means registers that can handle integer values, and inside floating point register or C1 we have floating point we have registers that can handle floating point values. Sorry, so let me write it again. As I said, so we have floating point register. Okay, in short, let's say register. So we have register file which handles integer value, and we have C1 or coprocessor 1 which handles floating point values, and inside C1 we have registers that can handle floating point values. These two register files, they share the same RAM or the memory. They share the same memory. So these are all memory that is our RAM. So they share the same memory, which means they share this register file. We all know that register file communicates data to and from RAM, and the same is true for floating point register as well. Also, between register file and coprocessor, communication is also possible, or data transfer is also possible. We all know that when we are transferring data from integer register or register file to the RAM, this is called store operation. And when you are reading something from the memory and bringing that value to the register file, this is called load operation. Now, similar to when C1 or floating point register reads something from the memory, this is also called load, but we add a C1 with it. And then when it transfers something to the register file, to the memory or RAM, this is again stored, but we add C1 with it. This C1 tells that this is an operation between the memory and coprocessor 1. Now, when there is a data communication between register file and C1, when something goes from the register file to the C1, we call it move to C1. This operation is moved to C1. When when data is transferred from the coprocessor to the register file, we call it move from C1. So these are the operations that takes place, and there are some instructions which are used. So let me discuss few of them. We already know load. load C1. So if we like to see the use of this instruction, let's say load C1 F1 0 SP stack pointer. So what this does is load a word from memory to a single precision floating point register. That means F1 register F1 will have a value coming from memory location SP. So this is what this instruction means. Now when we are discussing a load or store or any other instruction, one new thing that we discovered here, and that is F1. We did not see this notation previously. So before I go into the detail of the instructions, let's discuss where this F1 comes from. In C1 we have 32. In C1 we have 32 32-bit register where floating point value can be stored or can be handled. That means the number of registers in coprocessor are similar to the number of registers that you have inside the register file. The only difference is that in C1 the registers can handle floating point values. Also in register file we have different names for register. For example, T, S, V, A. But inside C1 the register names starts from register F0 and this continues till register F31. These are the 32 registers that we have inside the register file. These inside the C1 register file. So these register files can handle integer values as well as floating point values. So that means we in C1 we only have one naming convention, and that is F0 to F31. But in register file we have different names. We all know that there could be a register name starting with A, there could be register starting with V. We already know the T, we have S, and so on. But inside C1 all the registers are named with F. This F is for floating point, and this index are the number sequence in the register in their position in the register file. So 0, 1, 2, 3 up to 31. So there are these 32 registers. In previous slide we have seen a load instruction, one memory instruction where we are bringing something from the memory to the coprocessor. Now if you would like to bring something from the coprocessor to the memory, we would need to use a store, which is store C1. Now how the instruction works, we write store C1. Let's say we are trying to transfer the value of that is currently in register F5 to, let's say, this memory location. So what this instruction actually means? This means that memory location T2 plus 4 will hold the value that is in register F5. So this is what this entire instruction means. Now in the floating point operation we have two variations. One is single precision and the other one is double precision. So in single precision the values are 32-bit, and in double precision double precision, the values are of 64 bit. Okay. Now, how do we differentiate between a single precision operation and double precision operation? To do that, let's say we have an instruction which is add. Let's say we have an instruction which is add dot s. When we write this s, it means this is an addition operation, but it is a single precision addition operation. So we can write something like this. Let's say register f0, f1 and f2. So what this means is that whatever the value that we have inside register f1 and whatever the value that we have inside register f2, they will be added and the value will be transferred to register f0. But the result and the value that we are handling, all of them are going to be 32 bits. But if we write something like this, add dot d, this d indicates that this is going to be a double precision value, which means the value that we are going to handle are 64-bit values. So in this case, the instruction would look something like this. Now, what is the difference between the S dot S instruction and dot D instruction? Both of them are adds, and we did not have any variation when we are writing the registers. We did not find any variation. So, what is the difference? The difference is, see, the destination is f2, the source destination is f0, the source 1 is f2, and sorry, just made a mistake here, so this will be f4. So this will be f4. Now the destination is f0, source 1 is f2 and source 2 is f4. See the sequence f2, f4. So when we say double precision, that means we are dealing with 64-bit values. But when we are discussing about the register inside the coprocessor, we have said the registers are all of them are 32-bit. So how can we handle the 64-bit values? So when we have double precision operation, what it does, it takes two consecutive registers. Let's say this is F1 and F. Sorry, this is let's say this is a. This one is F2 and this is F3. So when we have F2 here, it automatically combines F3 with it. So this is 32-bit and this is also 32-bit. So if you combine both of these, that means we have 64-bit. So which means when we have source 1 equal to F2, that means automatically the instruction takes F3 and F3 as source 1. Similarly, when we have F4, instruction automatically takes F5 as source 2, and for destination, when we have F0, instruction automatically takes F1 as the destination. So this is how double precision values are handled. So we can have single precision variation of the or double precision variation of the same instruction. This is true for sub as well. Sub, you have single precision, as well as sub you can have double precision. So for all arithmetic operations, for any arithmetic operations, it could be multiplication, so mul dot s, or for double precision mul dot d. So all these operations have variation, single precision as well as double precision. So when the operation is single precision, only one register is considered, 32-bit one register, In the coprocessor, when double precision operation is considered, consecutive two registers are considered as destination or sources. What about the data movement instruction? One instruction that we already have seen in the diagram of the first slide, which is move from C1, and the other one is move to C1. So move from C1. Let's move from C1. If this is the instruction, so what would be the syntax of this? So move from C1 T0 and F2. So what this means is it actually transfers the content of F2 into register T0 and move to C1. What about the syntax of this one? Move to C1 again T1 F3. What this means is now register F3 will have the content of register T1. In both of these instructions, look carefully that we have written the register file register in the destination field, but in the first case, that means in this one, see the source is F2 and destination is T1 T0. In the second case, see the source is T1 and destination is F3. But this is the convention when we are using move command, that the register coming from the register file will go first and then the coprocessor register. These two instructions are used when you are moving data from register file to the coprocessor. But what about the data movement between coprocessor registers? So for that, what we use is MOVS, which is single precision. So in this case, how we can write in this case? So the instruction would be move dot s f naught f1. So what this does is move single precision data between two floating point register, moves data between two floating point registers, and move dot d move dot d here f naught, let's say f2. So in this case it moves double precision data between coprocessor registers. What about the type conversion instructions? We all know that register file holds integer values and coprocessor holds floating point as well as integer values. But if we have operations where there is a mix of data types, that means some of the data are of integer types and some of the data are of floating point type, what would we do? In that case, we need to convert all the integer type data into floating point values, and then we perform, for example, if it is arithmetic operation, then perform the arithmetic operation, and then if the final result is somewhere in the integer register, that means inside the register file, then we need to convert it back to integer values. So for that, so we need to do two things. One, we need to convert the integer value into floating point values, and then once we are done with the arithmetic operation that is in the floating point domain, and then we convert the floating point value back into the integer value. There are two instructions for that. One is cvt dot s dot W indicates integer value, and S we all know is single precision value. So what would be the syntax? Syntax would be CVT dot S dot W, and then we convert the value inside F2, which means F2 will hold a floating point value that is stored in F2, or in other words, the integer value that is stored in F2 will be converted into floating point value, and now will be stored in F0. Okay, and in the other instruction would be, let me erase this one and then rewrite it back. So this would be C V T W S, which means we are going from single precision to integer value. In this case, we are going from integer to single precision value. So the syntax would be CVT WS, and then let's say F1, and this would be F3, I'd say. So this would be F3. So what this means is register F1 now will hold whatever we had in F3. That means we had a floating point value in F3, and we are converting it back to integer value and storing it in register F1. So now F1 has integer value, and in this case F0 has floating point value. Now the question is, why we are not converting the floating point value into integer value initially and performing the arithmetic operation and storing the value directly to the integer register or register file? The answer is, let's say we have a floating point value 5.013. Let's say this is the value that we have. So if we convert it back to integer value, so if we convert it back to integer value, this would be 5.00 or 5, whatever it is. That means we are losing this 0.13. That's why if we have a value, let's say 5, inside our register file, and we sorry we try to convert it into floating point value, this would become 5.00. So we are not losing anything. That's why we convert all integer values into floating point value and then perform the arithmetic operation. Yes, there is a chance that if the final value after the arithmetic operation is something which is floating point, we might lose that value if we convert it back to the integer value, if the destination register of the final result is inside the integer register file or register file. We shall look into some arithmetic operation now, where we have mix of data types, integer types and floating point types, and we'll see how using the arithmetic instructions for floating point operations, how we can handle those operations. So the first the instruction is, let's say float x equal to integer y, and then float z, then integer y equal to float of x and float of z, and then float of z is equal to float of x minus float of z. an register assignment. X is inside the floating point register, so let's say it is assigned to register F0. Y is integer type value, so let's say it is assigned to S0, and Z again floating point, so let's say this assigned to F1. As you can see in the first case that y is integer and z is a floating point, so we need, and y is inside the register file as indicated by S0, so we need to transfer the value that is in S0 into the coprocessor register, which means we need to move. So move to C1, and what we are transferring, we are transferring the value that is inside the register S0 to where, let's say we are transferring it to register F2. So what this means is that now F2 will have whatever we have inside S0. Now the value that is inside F2 is integer value, but as you can see, Z is floating point, so we need to convert F2 into float, or the value that is inside F2 into float. So the instruction is CVT single precision S, and let's say F2 and F2. So we are converting the value that is inside F2 from integer to floating point and storing it inside the F2. Now we perform the addition operation, that means this addition operation. So we perform add dot s, and we are using F2 again as destination and F1 and then F2. So in this line F2 stores the value of F1 plus F2, both all of them are in floating point domain. Okay, now we perform another operation, which is add dot s f3 and then f naught and then f1. What this one does, this one stores if the value of f naught plus f 1. So I think I just made some mistake here. So we need to use this. This is the destination. Sorry for that. So because this line is the first one where the float x is inside. Now it makes sense. Now the third one is this one. Third line is sub. So sub dot s, and the result will be in f1, that is f naught f1. So what this one does, f1 will hold the value of f naught minus f1, and then we need to store this result into register S0, which is inside our register file, which means we need to convert the value that is in register F3 into integer type. So CVT will be converting it back to integer type from float, and then we'll have F3 and we'll store the result in F3. And from here let's write the remaining part here. where we'll transfer the value into move from C1, and where we are moving the value into register S0, and which value that we are moving the value of F3. So this is the entire code. This is how we can handle well when we have a mix of a mix of data types, and we are using coprocessor register file. We need to transfer everything into the coprocessor and convert all of the values into the floating point values, perform the arithmetic operation, and if we require the final result into a integer form, then we need to convert that the result into integer form, like in this line, that the result y needs to be in integer form. This is what we did here. We convert it into integer form and transfer the value from the coprocessor to the register file, and this is how the operation works.